Hi, everybody. Welcome to the HESI math review as you guys get ready to prepare for your HESI standardized test to get into nursing school. I want to go over a few of the most common things that you guys are going to see on that exam when it comes to the math section. That seems to be kind of the #1 section that people have an issue with because, let's be honest, nobody really likes math. But let's prepare you for that. So today in this video, guys, we're going to talk about fractions. When we discuss fractions, we're going to focus on how we add, subtract, multiply, and divide fractions. So I'm going to give you an introduction to what fractions are, what they look like, what they mean, just to get a better understanding of fractions because they tend to freak people out and I don't want that to happen. So let's take a look at how to work with operations with our fractions. Then we're going to dive into ratios and proportions. I'm going to show you how a ratio is very similar to a fraction. Once we understand fractions, we'll have a good understanding of ratios. And then once we set ratios equal to one another, we can use proportions. And I'll show you why we use proportions and how they can even be used for measurement conversion. So when we're converting teaspoons to milliliters or cups to ounces, there's a couple different ways that we can convert those. Once we kind of know what the measurement equivalents are, there's multiple ways to do it, and I'm going to show you those multiple ways, but we can also use proportions once we understand those. So that'll help us lead into those measurements. After we finish with measurements, we'll take a look at percentages. A couple different things we'll do with percentages, but actually in solving percents, you can also use proportions. So again, proportions are going to be kind of a common theme in these couple sections here. Because they're really easy to use. So I think you'll like those proportions and I'll show you what I mean by that. Then we'll get into more conversions. I know we talked about, we're going to get into measurement conversions. But when I say conversions right here, I'm talking about different forms of numbers. So when I have a fraction, what does that mean in terms of a decimal? If I have a decimal, can I convert that to a fraction? And so can I take a fraction and convert that to a percent? Absolutely. So let's take a look at that. When we get there, that's what I mean by that, the different number forms or, styles of numbers. Then we're getting into some basic algebra. The HESI covers kind of a broad spectrum of algebra, but really you guys are only going to see just your basic algebra. So how to solve for X, which we're actually going to do when we look at proportions, but a couple different ways we can solve for X. So I'll show you a couple different things with that basic algebra. And then we're going to get into military time. So when I say military time, some of you guys may be familiar with that as international time. We know that we use a 12-hour clock, right? That goes around twice in a day. We're used to our standard time, which means that we have an AM and a PM. On a military clock, it's simply just a 24-hour clock that goes around one time in a day. So you'll see times like 1500 and 1830. And you go, what the heck does that mean? I'll explain that when we get into military time. So a couple different things we're going to take a look at in this video, and hopefully this helps to give you guys a basic understanding of some of these things. And obviously, as you all go through this, feel free to fast forward through parts that you already feel pretty comfortable with, and stop and pause and do some practicing along the way if you need to as well, so that we can feel pretty comfortable and ready for our HESI. Okay, so let's get started. Let's start with fractions. All right. So with fractions, big thing to understand with fractions are simply just a part to total relationship. So if I had, 3/4, that fraction shows me that I have 3 out of 4 something, whatever it might be. I could be using pizzas, for example. I think I'm going to, whenever I talk about fractions, I use pizzas a lot because it's a great way to show a part to total relationship. Meaning that in a pizza, if I cut that pizza into 4 slices, that's my total, right? But I ate 3 slices. So I'm gonna shade out 3 there to show I had 3 out of the 4 slices. There is 3/4 of a pizza that I just ate. I mean, that's anytime. So the top number, guys, you're always going to refer to that top number as what's called your numerator. So if you ever hear me say the term numerator, that's your top number. Bottom number is called denominator. And that's going to be important when we get into addition and subtraction, because we're going to need to do something with that denominator. So numerator over denominator, like I said, fractions always represent a part to total relationship. So using pizzas, I'm gonna kind of stick with that theme to show what an equivalent fraction is. And there's a purpose for me doing this now, because this is going to help in addition and subtraction as well. So speaking of pizzas, we know when we order a pizza from any pizza place around town, we're gonna see that pizza usually comes to us sliced or cut into 8 slices. If I were to eat 4 of those slices, we know that we could then represent that out of, 4 out of a total of 8 slices. Which, looking at that visually, you can see that that is a total of half of that pizza, right? So what that means is 4/8 is equal to 1/2, meaning that if I didn't cut that pizza into 8 slices, if I instead just cut it into 2, I would have consumed the exact same amount in both cases. So even though these fractions look totally different, one says 4/8, the other one says 1/2. These are what's called equivalent fractions. And this is going to be helpful for a number of different things that we're going to do today. One, which I'm going to show you right now, how we reduce fractions. When we tell somebody how much pizza we ate today, if this was what we consumed today, I'm not going to say, oh, I had 4/8 of a pizza today. Oh, I feel so full. No, instead we're going to say, I had half of a pizza today. Oh my gosh, that was crazy. That's because we automatically reduce it to what's called its simpler form. So our simpler form means that it's just easier to kind of understand that that's half of the pizza. We don't need to think about it as 4/8. So here's what happens when you're reducing fractions. And this is what you're oftentimes going to want to do, because again, you're going to want to get that fraction to its simpler form. Without having to draw pizzas every single time, of course. Anytime you have a fraction, so let's take a look at that 4/8 again. If say you get to the end of a fractions question, so whether you're adding, subtracting, multiplying, dividing, and this is your answer you get, you typically want to reduce it. And when we reduce, what we're doing is we're taking it down to its simplest equivalent fraction. We're not changing it. Again, it still represents the exact same. We know the answer here is going to be 1/2. So again, I'm not changing the fraction. I'm still represented by the same exact fraction, but it's just its smaller form. So instead, what you're going to want to do, if the top number, again, your numerator, and the bottom number, your denominator, if both of those numbers can be divided by the same thing, where the answer comes out to be a whole number, meaning 4, I can't divide it by 3 because that's going to give me a decimal. Okay, so we want to make sure that we can divide both of these numbers by the same thing. In most cases, there might be a couple different options here. Yes, I can divide 4 and 8. I can divide them both by 4. All right, they're both multiples of 4. They're also both multiples of 2. Doesn't matter which one I pick. I can actually pick either one. As long as they can be divided by the same thing, you want to do so. And that's going to reduce it to a smaller form. It may not be its least smallest form, or it's very smallest form. Instead, it may be a smaller form, and we may have to reduce a little bit more. Let me show you what I mean. So like I said, 4 and 8, I can divide them both by 4. If I choose that, 4 divided by 4 gives me 1, so it gives me a whole number. 8 divided by 4 gives me 2, so that gives us our simplest form. I can't reduce that any further. If I was thinking, oh, 4 and 8, oh, that's not a marker. Let's say 4 and 8, just off the top of my head, I'm thinking, oh, they're both even numbers. I know I can divide all even numbers by 2. If I did that, that's totally fine. As long as you divide both the top and the bottom by the exact same number, you are reducing it correctly. And like I said, where it comes out to be a whole number. So 4 divided by 2 gives me 2. 8 divided by 2 gives me 4. This is correct. This is a reduced fraction. However, looking at this new fraction we have here, it looks like I can divide these again because I'm still dealing with 2 even numbers that can continue to be divided by 2 here. And we still get, let's see, 2 divided by 2 is 1, 4 divided by 2 is 2. I still get the same reduced fraction either way I do it. So as long as you're dividing both the top and the bottom by the same number, you're reducing correctly. So in any case, let's say I have maybe another example would be like 10/12. Let's say I have 10/12. Well, let's think 10, I can divide that by 10, right? Very similar to our last fraction. We could divide by the top number. 10 divided by 10 gives me 1. If I did that, then I'm going to automatically have my simplest form. However, 12 divided by 10 gives me 1.2. I can't use that because it gives me a decimal. I don't want to do that. It has to be where if I divide it, both answers end up being a whole number. So let's think again. 10 divided by 5, right, would give me 2. 12 divided by 5 is going to give me a decimal. That's not going to work. So our only option here, since they're both even numbers, is to divide them both by 2. 10 divided by 2 does give me 5. 12 divided by 2 gives me 6. I actually cannot divide 5 and 6 by the same number. So 5/6 is my most reduced fraction here. So that's our simplest form for this one. So like I said, we're gonna get a lot of practice with this today because we're gonna reduce at the end of every operation that we look at today. So those are every fraction we've looked at so far. The top number has been smaller than the bottom number. When the top number is smaller than the bottom number, those are what's called proper fractions. And a proper fraction, that's how we reduce. Sometimes you may come across an improper fraction. And let me show you what an improper fraction looks like. An improper fraction, as you can guess, the top number is bigger than the bottom number. And that happens sometimes too. At the end of an operation, we get to something like this. Now, I'm not sure exactly how the HESI is. Now, in some cases, you may get the answer choice of an improper fraction, where that's okay, as long as, again, it's reduced. 15 and 4 can't be reduced by the same thing. 15, I can divide that by 5. I can divide it by 3. I can divide it by 15. These are not options for 4, right? I can divide it by 4. Can't divide 15 by 4. I get a decimal. So this is its most reduced improper fraction. So if I wanted to, if you know, in some cases, like I said, HESI is okay with this. Sometimes you don't have to reduce it differently. You can leave it in its improper form. So if you get to an answer and you know you get an answer choice where the top number is bigger, that's okay. Sometimes they're okay with you leaving it in improper form. Sometimes they don't want you to leave it in improper form. They think improper, top number is bigger. Again, like I said, it's called improper. We don't want to leave it that way. So in the event that you don't see any improper fraction answer choices, it may be because it's wanting you to convert it to a mixed number. And here's how we do that. Pretty simple. Way to just better understand what 15/4 represents. Let's think about pizzas again. We have pizzas that are cut into 4 slices, right? Because there's our total. Our total is 4. So here's 1, 2, 3, 4. There's 4 out of 4. This simply just means that we have more whole pizzas. So here we have 1, 2, 3, 4, 5, 6, 7, 8 fourths, right? You see where I'm going here? 9, 10, 11, 12, 13, 14, 15. This last slice is missing. So here is a visual representation of 15/4. It simply just means we have 3 whole pizzas and then 3/4 of the last pizza. So you see where we're going to end up reducing this to 3 3/4. But like I said, without having to draw pizzas every single time, here's what we're going to do. We're simply going to look at this line right here between our numerator and denominator as a division line, as if it says 15 divided by 4. And you guys may be thinking, oh my gosh, we're getting ready to do long division. Not much, I promise. We're gonna stop at a certain point. All I'm asking here is how many times and you don't have to draw this out. You can just ask yourself using this, but how many times will 4 go into 15? That's what 15 divided by 4 says. If you do it in your calculator, 15 divided by 4, you're gonna get 3.75. That means it goes in 3 whole times. So 3 is our answer. And here's what we're doing. 3 is and I'm not going to use that 0.75. We'll get to that later, how 3.75 is the same thing as 3 3/4. But 3 is our answer because 3 times 4 is 12. If you guys are getting a memory jog about long division here. 3 times 4 is 12, which means since 15 minus 12 is 3, here's where that 3 3/4 comes from. My answer is my whole number. There's the 3. My remainder is the numerator of that fraction, and my denominator, which was 4, is simply just the same. So that's how we get that 3 3/4 from an improper fraction. All we're doing is we're reducing that improper fraction. So we'll do that a couple times today too. So that's how we reduce fractions, guys. Again, if you have a proper fraction or even an improper fraction, you can look at the top and the bottom and see, can I divide them both by the same thing? And you can reduce it that way. In the event you want to get improper fractions out of its improper form, then you do this. You simply just divide it. All right, so let's take a look. let's get into some addition and subtraction. Okay, so we're gonna start with addition and subtraction. We'll focus on those two together because we can approach those two operations the same way, and then multiplication and division can be approached the same way as well. So we're gonna group those two together, and those are actually a little bit easier than addition and subtraction. When we're adding and subtracting, no matter what, so anytime you're adding and subtracting, I'm just gonna abbreviate here, add and sub. Anytime you're approaching fractions with addition and subtraction, your first step, you need, I'm gonna write common denominators. So we need to have common denominators. Here's why. Here's what happens. If I'm adding together, let's total up how much pizza me and a friend had, let's say. So we're eating a piece or a whole pizza here. Again, we got it from Pizza Hut and cut into 8 slices for us. I had 2 slices. So I had 2 out of the 8 slices. Okay. Whereas my friend, she had, let's say she had 3 slices. So she had 3 out of the 8 slices of pizza. So if we're adding together in terms of fractions, what we had together, I had 2/8, she had 3/8 together, as you can see visually here, we had 5 out of the 8 slices of pizza. So you can see what happens with addition. When we're adding fractions, all we're gonna end up doing is adding their numerators together. That's where that 5 came from, and the denominator just stays the same. So that's what I mean by we have to have common denominators. So here in this case, it was already common for us, so we went ahead and just added those numerators together. Always pay attention to the end to see, can I reduce this answer? I could not here. 5 and 8 cannot be divided by the same thing, so 5/8 is a reduced fraction. Okay, so that's what we're gonna do. We're gonna add those fractions together that way. If I had, again, the fraction, let's say, 1/6 plus, well, let's not do that yet. Let's say 1/6 plus 2/6. It gives me 3/6. All I'm doing is adding the 2 top numbers together, and then the denominator stays the same. Make sure we can reduce if we reduce if we can. 3 and 6, absolutely, both multiples of 3. So let's go ahead and divide them both by 3 to get 1/2. Right? 3 divided by 3 is 1, 6 divided by 3 is 2. Okay. What do we do when they're not the same? Let's take a look. Let's say instead we had, in that last problem, we had 1/6, but instead we were adding that to, let's do something simpler here. Let's say 2/3. 1/6 plus 2/3. Here's what we want to do. We're going to go back to what I first showed you at the beginning of this video when I showed you equivalent fractions. Remember, I told you that fractions can be looked at differently. Without changing them, I should say without, I guess, changing the fraction itself, we're simply looking at it differently. But it's still it's a representative of the same number. So, like again, think in terms of pizza, right? We said 4/8 of pizza is the same thing as 1/2. So we can use a different fraction in place of it, and that's what we're going to do here. So I want to make sure both of these fractions have the same denominator. So what I'm going to do first, I'm going to look at my 2 denominators that I have, 6 and 3. What I want to do is I want to find their least, what's called their least common multiple, not factor. A lot of you guys jump to, if it was 3/6, you're right, we could divide them both by 3. So a lot of people want to say 3. That's called a factor. That's what you're dividing by to reduce it. 3 is a factor of both of these. But in terms of multiples, we're actually thinking of these 2 numbers and bigger. So think of like your times table, right? So I'm going to look at my times table for 3 and for 6. Meaning I want to look at both these numbers times 1, times 2, times 3. I'm not going to have to go this far. So let's take a look and I'll show you what I mean. Let's see, 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. I could go on and on forever, but let's stop and let's take a look at the multiples of 6. And we want to take the first one that they have in common. So let's look, 6 times 1 is 6. I've already found it. We're going to have more in common. They're going to end up sharing a couple different multiples as we move on further down the road here. But I want to use their least common multiple because that's going to help us from having to reduce less later. We're not gonna have to reduce as much as long as we use the smallest multiple that they have in common. So here it is, we found it. Both 3 and 6 have a shared multiple of 6. So what that means, why do we do that? What that means is I want both of these fractions to have a denominator of 6. One of them already does. What that means is nothing about that fraction is going to change. Since it already has the denominator 6, the numerator doesn't change. But here in the second fraction, I am changing that. I'm changing the denominator from 3 to 6. So all we have to do is do the exact same thing. Whatever we did to that bottom number in terms of that multiplication, we do the same thing. So 3 became 6, because if you think back to that times table, it was 3 times 2 that gave me 6, right? Well, as long as I do the same thing to the top, we're keeping that fraction equivalent. So 2 times 2 gives me 4. So here, what this means is 4/6 is the exact same fraction as 2 over 3. We're just using this in place of this so that we can add these two numbers together. And that is exactly what we can do now. And now that I'm representing this with 4/6, I can add my two numerators together. 1 plus 4 is 5, and 6 stays my denominator. So I get 5 over 6 as my answer. In some cases, you might end up having to change both of your fractions. So here, we only had to change one of them because our least common multiple happened to be one that already existed. But let's say instead of 2/3, we were adding, let's say 1/6 plus 3/4. In this case, when I look at my common multiples for 4 and 6, it's not either one of those. So let's take a look. I'm going to look at my times table again for 4 and for 6. I'm going to start with 6. Sometimes it's easier to look at that bigger number first. Like I said, we're looking times 1, times 2, times 3, times 4. And let's stop and look at that here. 6 times 1 is 6. 6 times 2 I know is 12. 6 times 3 is 18. Let's take a break here and let's look at 4. All right, what's 4 times 1? 4. What's 4 times 2? 8. 4 times 3? 12. There it is. The very first one that they have in common is 12. So here again, here's what that means. I need to change both of these fractions now to have that common denominator. 6 is going to become 12 and 4 is going to become 12. Now they're totally different. So we have to look at them one fraction at a time. And remember, whatever you do to the bottom number, you have to do the same thing to the top. So 6 became 12. Because again, 6 times 2 is what gave me 12. So whatever I do to its bottom number, I have to do the same thing to its top number. And 1 times 2 gives me 2. So 1 over 6 becomes 2 over 12. Now looking separately at the 3/4, 4 became 12. Remember, 4 became 12 when we were multiplying by 3. Since we multiplied that bottom number by 3, we have to do the same thing to the top. 3 times 3 gives me 9. So now I can add these two fractions together. 2 plus 9 gives me 11, and 12 stays my denominator. I cannot reduce 11/12, so I coincidentally cannot reduce this. Just like our last question there, I can't reduce this because 11 and 12 can't be divided by the same thing. I get 11 over 12. Okay. Always need common denominators when we're adding or we're subtracting. And don't be thrown off if you ever see mixed fractions. If this was, I'm going to leave this here for a second just to show how it's very similar. Actually pretty easily done here. If instead of 1/6 plus 3/4, let's say this was 5 and 1/6 plus 2 and 3/4. No big deal at all. In addition, what you can actually do is you can separate the whole number from the fraction. So meaning I can look at that 1/6 and the 3/4 by itself, just like we did over here. Focus on just the fractions and get the fraction answer, and then put it together with your whole number answer. So here, if this was our problem, we would have isolated the 1/6 and the 3/4, went ahead and added those two together first. Since we did, we got 11 over 12. Now we simply just add the whole numbers together. 5 plus 2 is 7. That makes this, excuse me, 7 and 11/12. We get 7 and 11/12 here. That's our answer. So don't be thrown off by those mixed fractions. And then again, subtraction, guys, is actually going to be the exact same. With subtraction, the only difference is you're subtracting those top numbers instead of adding those two together. So instead, let's say we have, and I'll use mixed numbers just to show kind of same concept here. Let's say we have 8, and let's do, how about 8? Let's do 3/5, and let's subtract, let's say 4 and 1. Let's do 1/3. Okay. All right, so let's take a look at this. So again, subtracting, like I said, with addition and subtraction, you can isolate those whole numbers and those fractions separately. So I'm going to focus on just the 3/5 and the 1/3 here. And I'm going to come back and get that 8 minus 4. We know 8 minus 4 is going to be 4. We'll come back to that. We'll add that later. So for now, let's look at just the 3/5 minus 1/3. All right, again, they're not the same. We need a common denominator. So let's look at our times table for 5 and for 3. So 5, multiples of 5, we know 5, 10, 15, 20, right? 5 times 1 is 5, 5 times 2 is 10, times 3 is 15, times 4 is 20. Let's stop and let's look at 3. 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15. There's the first instance we have where we have a shared denominator. Happens to be the same case if I were to just multiply those two numbers together. Sometimes that works. Sometimes it's the only thing that works. We didn't want to do that with our 6 and our 4 in our last example, because 6 times 4 is 24. That's a huge number that we would have reduced later at the end. It would have worked. So you can do that where you just multiply the two denominators together, but I don't recommend it. If you can find something smaller, you want to stick with that smaller number. So the 12 worked better in our last example. Here, it just so happens to be that the very first one that they have in common would be as if I'd multiplied those two numbers together. So we're going to use 15 here, because that is our least common multiple. So that means I need to change both of these to become something over 15. So remember, focusing on one fraction at a time. Whatever you did to that fraction's bottom number, you do the same thing to that fraction's top number. So I'm not looking at this 1/3 right now. I'm only focusing on the 3/5. Since 5 is changing to 15, remember that was we multiplied that by 3 to get there, right? 5 times 3 is what gives me 15. So we have to do the same thing to the top, and that gives me 9. Now looking at the 1/3, 3 is changing to 15. 3 times what gives us 15? 5. So we do the same thing to the top number. 1 times 5 gives me 5. So now I have two fractions with a common denominator, and I can go ahead and subtract. Like I said, the only difference between addition and subtraction is I'm now subtracting those numerators. 9 minus 5 gives me 4, and then 15 stays my denominator. Can 4 and 15 both be reduced by the same number? No. 4 I can divide it by 4, not 15. 4 can be divided by 2, but not 15. So 4/15 is a reduced fraction. Now all we need to do is go back, and like I said, we're going to go back and get that 4, because again, my whole numbers, don't forget those guys. 8 minus 4 is 4, and then we just simply put that together with our fraction answer. So my total answer here would be 4 and 4/15. Okay, your subtraction. So not to be, again, hopefully not too bad. We just need to focus on those denominators. Big first step with addition and subtraction are common denominators. So make sure you focus on that. Multiplication and division, a little bit different. Multiplication and division, you do not have to have common denominators. I mentioned earlier that multiplication and division is actually a little bit easier than addition and subtraction because of that. Because you don't have to change your fractions too much where we're having to have common denominators. Instead, in multiplication and division, you're still just using your fractions, but you're just multiplying those two straight across. You're going to multiply your two numerators, multiply your two denominators. So if I have 3/4 times 1/5, all I'm doing is going straight across. 3 times 1 is 3. 4 times 5 is 20. My answer is 3/20. It is a reduced fraction. I told you earlier we get a lot of practice with reduced fractions, but we end up having a lot of reduced fractions at the end. Let's do one where we're not gonna be reduced. Let me show you a trick that we can use actually in multiplication and division here. Let's say I have, let's use 4/5 times 2/8. Okay, let's multiply straight across here. 4 times 2, again, that's all we're doing. Multiplication, we're just going straight across. 4 times 2 is 8. Down at the bottom here, 5 times 8 is 40. Can I reduce this? Absolutely. I can reduce it a couple different ways, right? 8 and 40 are both actually divisible by 8. So I can divide them straight away. Anytime you can divide both numbers by the top number, you're automatically going to get your most reduced form, because the top number divided by itself is 1, and you can't get any smaller than 1. So 8 divided by 8 is 1, 40 divided by 8 is 5. So my answer is going to be 1/5. If you didn't think about that and said, you know what, I have 8/40ths, well, 8/40ths, both are even numbers. If you started off with 2, that's okay. Remember, as long as you're dividing them both by the same number, you are reducing it correctly, and that is totally fine. Let's do that. 8 divided by 2 is 4. 40 divided by 2 is 20. This is a correct answer, but we're just not completely reduced. 4 and 20, I can divide those both again by 2, or maybe now you're looking at it and you can see, oh, they're both divisible by 4. If you chose to do that, dividing it by 4 gives me 1/5. Or again, if you chose to just keep going by 2, you would have gotten 2/10. Would be able to see that that can be divided by 2 again, and you get 1/5. So you want to go to where you just can no longer divide any further, and that's when we get here, 1/5. But a little trick in multiplication, this is a correct way to do this. Just multiply straight across and reduce at the end. But in multiplication, if you want to, you can actually reduce before you multiply. And here's what I mean by that. Let's go back and look at the original problem here. 4/5 and 2/8. Well, 4/5 is already reduced, so I can't do anything there. But if I wanted to, I could go ahead and reduce 2/8 here. Okay, 2/8, if I wanted to, I could say, well, 2 divided by 8, sorry, not 2 divided by 8. 2 and 8 are both multiples of 2. So I could actually go ahead and divide those both by 2 and get 1/4. So 4/5 times 1/4 is still going to give me the same answer here at the end. Another trick you can use is actually you can reduce opposite numerator denominator too, whether it's in the original one or even now that I've created this new, I said that 2/8 is the same thing as 1/4. I can even reduce again by looking at opposite numerator denominator here. 4 and 4, both divisible by 4. I can go ahead and cancel those two out, essentially, because 4 divided by 4 is 1, and 4 divided by 4 is 1 there. Multiplying straight across gives me 1 times 1, 5 times 1. I get my reduced answer. And again, you don't have to do that. That is simply just, if you choose to do so, you can reduce across with opposite numerator denominator. We couldn't with 2/5 or 1/5, however we do it. But that's the benefit to multiplication there, is you can reduce beforehand, and you can even reduce a couple times beforehand if it's easier to work with those smaller fractions ahead of time. Sometimes you end up with big answers with large numerator and a large denominator, and you have to, really reduce that a lot. So sometimes it helps to go ahead and reduce that at the beginning, since you're dealing with one fraction at a time. But totally up to you. You don't have to. So here's the thing with multiplication and division. So that you're like, okay, that's easy. I can do that. I'm just multiplying straight across. That's true. That's all you're going to do. But remember that not all fractions look that way. Not all fractions are just numerator over denominator. Occasionally, you may come across a whole number. If I have 6, what does that mean? Well, if you ever have run across a whole number, you can actually turn this into a fraction. 6/1, if I were to reduce 6/1, it would be 6, right? Think of it as an improper fraction. 6 divided by 1 is 6. All I'm doing here by putting a 1 under it is I'm providing it a denominator so that I can multiply straight across like I've done before, like we did in the last couple examples there. So anytime you come across a whole number, feel free to just add a 1 under that, and that makes it easier to then multiply. Some fractions, you might have a whole number with a fraction. That's again called a mixed fraction. So if you ever saw something like this, 5 1/2, I can't go straight across here, because if I did, you know, I just use the 1 and the 2, I'm excluding the 5. This whole thing is one number, and it needs to be just a numerator over a denominator. So earlier, if you remember when I said that we could reduce an improper fraction, right? 15/4, I'm going back to what we did with reducing. 15/4, guys, remember 15 divided by 4 gave me 3 with 3 remaining, and 4 stayed the denominator. So these two are actually interchangeable. In this case, I want to take that mixed fraction and I want to put it back in that improper form because it's going to be a numerator over denominator. And that's what I want. In multiplication and division, I simply just want two numbers. I want a top number and a bottom number so that then I can go straight across. That's the idea. So 5 1/2, how do we do that? How do we make these interchangeable? How do we go back to that improper form? All we're going to do to take a mixed number and put it in improper form, you're simply going to take the whole number, multiply by the bottom number. Seems weird. We're going in this kind of counterclockwise direction here. 5 times 2 is 10. So there's my numerator, or my whole number times my denominator. We're going to then add that numerator. So we multiply, then add. 5 times 2 is 10, plus 1 gives me 11. And that denominator simply just stays the same. Just to show you that that worked, remember, here was the example that we used earlier when we reduced 15/4 to 3 3/4. Let's say we wanted to go back to that form. Well, 3 times 4 is 12, right? Plus 3 is 15/4. So mixed fractions, again, we're interchanging them. We're not changing this number at all. I'm simply just changing it to a different form of that number. So 5 1/2 is the same thing as 11/2. So in the event that I had 5 1/2, let's say 5 1/2 times 6, is the example we just saw a second ago. Well, in order to go straight across, I need to put this in numerator denominator form. So 5 1/2, we just changed to 11/2. Remember, with the whole number, we give it the denominator 1. Now can I go straight across? Absolutely. Now I can go straight across. 11 times 6 is 66. 2 times 1 is 2. So I can go ahead and reduce this. Again, this is going to be kind of easy here. 66 divided by 2 is 33. So I end up with the answer 33. Okay. And again, if you wanted to, don't forget you could have reduced here at the very beginning. 6 and 2, both divisible by 2. I could have changed this to 1 and this to 3, making it 11 times 3, which is 33. And your fraction answer doesn't have to be a fraction. Your answer can be a whole number. That's okay. It doesn't have to be 33/1. It's okay. All right. Okay. So that's the thing to remember with multiplication, and really with multiplication and division. So just a little note like we did earlier with addition and subtraction, but for multiplication and division, really your first step, like again, for addition and subtraction, it was making sure we had the common denominator. Here, your first step is making sure we are in numerator, I'm gonna write numerator over, well, if I can spell, denominator, denominator, sorry, numerator over denominator form. It has to be in that form. This fraction, good. It's in numerator denominator form. This fraction, good. Numerator denominator form. The whole number. All we're going to do, remember, is put it over 1. Now we're good. A mixed number, if I had the mixed number 2 and 3/5, let's put it in numerator denominator form. 2 times 5 is 10, plus 3 is 13. 5 stays our denominator. Now we're good. Anytime you see multiplication or division, we need to put it in numerator denominator form, because again, all we're going to do the next step is just go straight across. We're going to multiply our two numerators, multiply our 2 denominators. So if I had, let's say, 3 1/4 times, I don't know, let's say 2/3, or something small here. Again, this one's in the proper form that I want it to be in, so I don't have to do anything to that, but 3 1/4 I do need to change. 3 times 4 is 12, plus 1 is 13. 4 stays my denominator. Like I said, 2/3 stays the same. So I'm going to go ahead and go straight across. All right? 13 times 2 is 26. Down at the bottom, 4 times 3 is 12. So remember, keep in mind that again, I'm not as familiar with HESI on what they're looking for if they're accepting improper fractions. If they do accept an improper fraction, they would not accept this because it's not fully reduced, right? They're both even numbers. I can reduce them by 2. If I chose to do that, let's divide them both by 2 to reduce that. 26 divided by 2 is 13. 12 divided by 2 is 6. So I end up with that reduced number, or that reduced fraction 13 over 6. This might be an acceptable answer on the HESI. Some places accept those improper fractions, and some, again, want it to be out of that improper form. If that was the case, we're gonna just divide. Remember, we're looking at improper fractions using division. 6 goes into 13 twice, because 6 times 2 is 12, so that gives me a remainder of 1. So writing that in a mixed fraction form, my answer is my whole number, so 2. My remainder is the numerator of my fraction, and my denominator just stays the same. So my answer here would be 2 1/6. And you could have gotten that from the 26 over 12 as well. If I chose to just stop there and say, well, it's in improper form, let's take 26 divided by 12. Totally fine. 12 goes into 26 twice because 2 times 12 is 24. So I get a remainder of 2. So my answer, remember, is my whole number. My remainder becomes the numerator of my fraction, and my denominator stays the same. So this is correct. However, let's look at the fraction portion there. The fraction portion of that answer can be reduced. And if that's the case, we need to reduce it. 12 and 2, or I'm sorry, yeah, 2 and 12 there are both divisible by 2. So that gives us 1/6, again, making this total answer 2 1/6. Always reduce. Always want to make sure your answer is reduced at the end. Okay, that's multiplication. This exact same first step applies for the division as well. Here's what happens in division. In division, we're actually going to pretty much turn it into multiplication. And here's what I mean by that. In division, if this was a division problem, I'm going to do the same thing. I first want to put it in numerator denominator form. So 3 1/4 became 13/4. 2/3 stayed 2/3. So we followed the first step. But in division and division only, we're going to apply what I call KCF, or keep, change, flip. In division, what we're going to do is we're going to keep the first fraction the same. It's always keep. The first one is keep. So that one stays 13 over 4. When I say change, we're changing division into multiplication, and we're going to flip the second fraction. You're always just flipping the second fraction. So that 2 over 3 becomes 3 over 2. And then now you multiply straight across and get your answer. So 13 times 3 is what? 39. And then multiplying down here at the bottom, 4 times 2 is 8. So I actually cannot reduce that if I were to leave it in improper form. I'm going to go ahead, if I want to make that a mixed fraction, remember 39 divided by 8. 8 goes into 39 4 times, because 4 times 8 is 32, giving me a remainder of 7. So that becomes 4 7/8 as my answer. So you see what we did here? All we did with multiplication and division, we want to first make sure it's in that numerator denominator form. If it's not, put it there. So put it in numerator denominator form. If it's multiplication, we're going to go ahead and multiply straight across. If it's division, you're going to turn it into multiplication and go straight across. But how you turn it into multiplication, you have to be very specific on how we do that. We make sure we keep the first fraction, we change it, but then flip the second fraction. Some people were taught in division of fractions, you're going to multiply by the reciprocal. Reciprocal just means flipped version of that fraction. But it's always the second fraction. So keep that in mind. Okay. And that's fractions, guys, in a nutshell. You know, so the big thing to remember with fractions, again, most important for addition and subtraction, you've got to have common denominators. Multiplication and division, you've got to have that numerator denominator form. And then you follow your next steps. Okay, let's get into next. We're looking at ratios and proportions. What I mean by ratios, guys, a ratio is very, very similar to a fraction, right? That we have the fraction, this is just a common fraction, so I keep using that, but 3/4 is actually, when we get into conversions of our forms of numbers, you're gonna see that 3/4 is the same thing as 3/4. That's how we say a ratio out loud, 3/4. We use them very differently though. A fraction oftentimes is used as a part to total relationship to show that we have 3 out of 4 something. Ratios are typically used in a comparison relationship. Again, like I said, we say it out loud as 3/4. So instead of saying we have 3 boys out of the 4 total people in the classroom, this is showing that maybe I have 3 boys to every 4 girls. So meaning there's a total of 7 in the classroom. Or again, it's a reduced ratio. Maybe I have 35 in the classroom and my ratio though is 3/4. So because again, ratios can actually be reduced the same way fractions can be reduced. And for the purpose of when we get into proportions, we're going to look at it very similar. We're going to take ratios and even look at them as fractions. So like I said, they compare, they're very, very similar in terms of when we're just discussing numbers. 3/4 is going to convert to 3/4 when we're looking at converting a fraction to a ratio. But like I said, they're just used very differently in life situations, if that makes sense. So that's a ratio. Okay, so a ratio, if I said to take a ratio and a fraction that's like 5/8, for instance, and I said write that as a ratio, I'm simply going to put that 5, that numerator, put a colon mark between it, and then that denominator second. So again, we just look at it as 5/8 instead. So that's where we use ratios, but here, and that's the extent of what we're going to get into with ratios. That's it with ratios. Ratios are more common in terms of the HESI, and in terms of we're going to see those in math is in a proportion. Here's what I mean by a proportion. A proportion, very similar to what we looked at with equivalent fractions, right? We saw the relationship of our pizzas, right? We said 4 out of the 8 slices of pizza is equivalent to just half of the pizza, right? 1 out of 2 slices if I were to just cut it into 2. This is actually a proportion. Even though it's not written as ratios, if I wrote it as 4/8 and set it equal to 1/2, these are the same. So this is just the same thing. All it means is I'm saying that 4:8 the same way 1:2. So a proportion is said out loud as that way. It says we're saying 4:8 as 1:2. It's the same way as saying big is to small, as hot is to cold, right? The relationship on this side of the equal sign is equivalent to the relationship on this side of the equal sign, right? So that's what a proportion is. And proportions are only proportions if they are actually equal to one another. So 4:8 as 1:2. I could not say 5:8 as 1:2. That's incorrect. That's not, because those aren't equivalent fractions, right? 5/8 is not the same thing as 1/2. So that's what a proportion is, and I'm going somewhere with it, I promise. There's a reason why we look at proportions and why they can be pretty helpful. And oftentimes you'll see me today probably rewriting these ratios as fractions because we're kind of more familiar with fractions and they're kind of easier to work with. So I'll show you what I mean by that. But in a proportion, so how that works. So let's take the same proportion we just looked at. We were saying 4:8 as 1:2. I'm going to go ahead and write those as fractions. I'm going to show you why. How we can test to see if a proportion is equal. So if these 2 fractions, off the top of our head, we know that these 2 fractions are equal to one another. But if I wanted to test to see, are these fractions actually equal to one another? We can cross multiply. I can cross multiply opposite numerators and denominators. And if I get the same answer in both cases, then it's true. It is equal. So I can multiply, and it doesn't matter what side you multiply first. All we're doing is testing to see if we get the same number. 8 times 1 is 8. Over here on the other side, 4 times 2 is 8. That does make this an equivalent proportion. There are 2 equivalent fractions or 2 equivalent ratios. That in turn means this is a true proportion. And again, I'm going somewhere with this. There's a reason why we're going to do this. Let's test another one. Let's say we have 3/5 and we have it set equal to 2/10. I don't know. Let's check to see if these are equivalent. Well, let's cross multiply. 5 times 2, like I said, Doesn't matter which side you multiply first, but 5 times 2 is 10. We already know that's not gonna be equivalent because 10 times 3 is 30. This is not equivalent, so therefore this is not a proportion. Just FYI, if you ever come across something like that, and it may be written as ratios, you know, you may see that that ratio was written as 3:5 as 2:10. If you see it this way, feel free to just rewrite those as fractions so that you can cross multiply, or doing the same thing we did here, multiplying the two inner and the two outer numbers, sometimes referred to as the means and extremes. Means and extremes just means the means are the two inside numbers, extremes are the two outside numbers. It's doing the same thing we just did over here. 5 times 2 is the same thing as 5 times 2, right? Which gave us 10. And then 3 times 10 is the same thing as 3 times 10. So if you want to leave it in that ratio form, you can see what I mean. We're going to get the same answer either way. Some people would prefer to see those as fractions, so we go ahead and rewrite those as fractions, as that's what I do. But if you leave it in this form, you can just do that. Multiply the two inside numbers and the two outside numbers. Okay. All right. Here's where I'm going with this. In a proportion, if you're ever missing a number, you can use what we just did with that cross multiplication method to figure out what that missing number is. So here's what I'm going to go back to the 4/8 and the 1/2 to show you, just because we know what those two fractions are. But in the event that part of that ratio, or I'm sorry, part of that proportion is missing, we can solve for that. So let's say we have 4:8 as x is to 2. We know that's going to be 1, right? Because again, a proportion says 4:8 as x is, or as what is to 2 is what we're saying here. Well, again, we see that there's a 4 is half of 8. So we know that the equivalent, or the relationship over here, must be equivalent to the relationship over here. Well, we know 4 is half of 8. So whatever this is must be half of 2. So we know that's going to be 1. So sometimes it's easy just to do that in our head. But if it's not, we can use that cross multiplication method. So bear with me for a second. I'm going to show you why that works, and then I'm going to show you a shortcut. I'm going to show you a shortcut and how we can solve proportions very quickly. So what that means is if we cross multiply 8 times x, I don't know what x is. It's an unknown number. Again, we know it's 1, but let's pretend like we don't. 8 times x, we can just call it 8x, because I can't multiply by a letter, right? It's just going to be 8x. That's what we're going to call it. That represents 8 times x. On the other side, I'm going to set it equal to my answer on the other side. 4 times 2 is 8. So now I have just a really small kind of pre-algebra problem. We'll get to algebra a little bit later too. Pre-algebra problem here that says 8 times something is equal to 8. Again, this one's an easy one that we can do in our head. They may not always be this easy, but we know 8 times 1 is 8. So we know that our answer is going to be 1 here, but pretending like we don't, here's what happens in pre-algebra. Whenever you have a letter multiplied by a number, in order to get rid of that number, so we want it to just say x is equal to something. So I need to get rid of that 8. Since 8 is being multiplied by x, we're going to do the opposite of that, and I'm actually going to divide. By doing the opposite, it helps us to kind of cancel it out. So that's what we're going to do. I'm going to divide by 8. And that's exactly what we're doing here. You can kind of see it almost looks like the fraction 8/8, which we know is 1. And 1 times x is x. So that's exactly what's happening here. I'm canceling that out. But remember, whatever you do on one side of the equal sign, you have to do on the other to keep it equal. So 8 divided by 8, we know is 1. So there's my answer. So like I said, I told you guys, bear with me for a second and I'll show you guys a shortcut, because what actually works in proportions every single time, you notice what we did is we took the answer. So our 8 right here was 4 times 2. We took the answer to that side and divided it by this. So every single time that's going to work. If you take wherever x is in your proportion, if you multiply the opposite side and then simply just divide by the last number. So here was the proportion we just had up on our screen here. If I multiplied opposite of where x is, so 4 times 2 is 8, and then divided it by 8, I'm going to get 1. And that works no matter where x is in your proportion. Let's pretend, since we're pretty familiar with this proportion here, let's pretend that this is missing, that it's x over 8 is equal to 1/2. Like I said, again, this one's kind of an easy one. We know that 1/2 is half. So 1 is half of 2, so therefore whatever this is must be half of this number. We know it's 4, but let's pretend. So let's cross multiply. Since x is over here, I'm gonna multiply, and let me use a different color here to show. I'm multiplying 1 times 8, which we know is 8. And then I'm simply just gonna divide by the last number there, and that gives me 4. So my missing number is 4. Works every time. Anytime you have a proportion with a missing number in it, simply just cross multiply and then divide by the last number. If I have 4 over x is equal to 1/2. We know 1 is half of 2, so 4 must be half of this number. You know, it's 8, but let's cross multiply. Opposite side here, 4 times 2 is 8, then dividing that by 1, 8 divided by 1 gives me 8. So my missing number is 8. And that works every single time. Let's say I have, about 5/6 is equivalent to x over, let's say, I don't know, let's say 24. And I'll show you this one, because what happens here, you may be able to look at this and say, well, I know fractions. I know that 6 to 24, if I'm thinking of equivalent fractions, right? I know that in order to get from 6 to 24, I multiply by 4, right? If I do the same thing to the top, I'm going to get 20, because 5 times 4 is 20. You'd be correct. That's also a way that you can do that, but sometimes it's not as easy. Sometimes you may end up with decimals and things of that nature. But you would see if we were to go ahead and multiply here 5 times, I don't know, 5 times 24 off the top of my head. 5 times 24 is 120. If I were to multiply again across, 5 times 4 is 120 divided by 6. 120 divided by 6 gives me 20. So my answer here, x is equal to 20. That, like I said, that would work. But again, you could also use the cross multiplication method. That's the beauty of math, is you can get the same answer multiple ways. Sometimes it's not as easy because there's not always a whole number multiple to get to that. So here's what I mean by that. If I said instead, if I had 5/6 is equal to x over, let's say 15. Well, 6 to 15, there's not an easy multiple here. 6 times 2, no, 6 times 3, no. So instead, it's easy to use this cross multiplication method because this means we're probably going to end up with a decimal answer here. So 5 times 15, if I were to multiply 5 times 15, that's going to give me 75. And then 75 divided by 6, again, because that's our method here, cross multiply, then divide by our last number. 75 divided by 6 gives me 12.5. So in this case, x is equal to 12.5. And that's okay. X can be a decimal. It just simply means that the relationship over here is equivalent to the relationship over here is 12.5. It doesn't necessarily have to be in, a whole number over a whole. So don't think in fractions where we want a whole number over a whole number. Here, we're simply just looking at this as a relationship of numbers, not necessarily as the fraction like 12.5 over 15. I know that seems weird. We're simply just trying to find that number, the missing component. So the missing number that makes this equivalent to this. So don't think of it in terms of fractions, just trying to solve whatever x is. So x can definitely be a decimal here, because again, remember, that's the same thing as saying 5 is to 6 as what is to 15 is what we just did. So we're just looking for whatever that what is. And in this case, it was 12.5. So those are proportions. Proportions are going to help us with a lot of different things using that exact same method, that cross multiplication method. Because again, what we can do, or not again, I haven't mentioned this to you guys, but we can use that cross multiplication method because what that represents is, the side of the fraction that has the 2 numbers on it, or the side of the proportion that has the 2 numbers on it, we can look at that as what we know, right? I know 4 over 8. I know that that's the relationship I'm looking for. This side is my unknown, because it has the x in it. I'm trying to solve for that. So that's my unknown. So by putting them equal to one another, we're saying, well, I know the relationship on this side, but I'm saying it's equal to this, I can solve that. I can, by putting the known equal to the unknown, I can cross multiply and solve that. So there's my unknown here. And why that's important is because we can use this in relationships with measurements. So just kind of getting into our measurements here. Let's think of something that we're pretty familiar with. We're pretty familiar with, let's say feet and inches, right? A lot of us, we're pretty familiar with a foot, right? A foot is equivalent to 12 inches, correct? So let's say, we know that's our known. Our known, we know that 1 foot is 12 inches. If I were to set that equal to, let's say I have 3 feet. What is that in inches? And off the top of your head, guys, you may be going, well, I'll just take 3 times 12. That is correct. And that's what we're going to do here. Because you're thinking, well, okay, if 1 foot is 12 inches, that means 2 feet is 24, 3 feet is 36. Okay, that's easy. Yes, we might have some that are just that easy, but sometimes we might have some that are not as easy, and why that cross multiplication method is going to be really helpful. So that's what we've done here, is we've said, well, here's what I know. Here's my known, right? I know that 1 foot is 12 inches. This is my unknown. Well, unknown. I don't know how many inches are in 3 feet. So by setting them equal to one another, I can say, well, 3 times 12 is 36 divided by 1. My answer is 36 inches. 3 feet is 36 inches. Maybe one we're also pretty familiar with. How about time, right? I know that 1 hour is 60 minutes. Let's say I want to know, well, how many hours is that if I have, let's say 180 minutes? Well, again, same exact, you can see what I've done here. Here's what's going to end up being important in these proportions when we're using them as measurements. You can see that I didn't write this 180 on the top. That's because, again, thinking of these as equivalent fractions, the relationship over on this side needs to be equivalent to the relationship on this side. So you can see that since I have hours to minutes, this side also needs to be hours to minutes. So my question here is, how many hours are 180 minutes? So that's why the 180 is on the bottom, because it's across from the minutes over on the other side. The relationship needs to be the same. Okay, so that's going to be pretty important in these proportions when we're using them for measurement conversions. So same thing we've done to solve that. Again, you guys might be thinking, well, 60 to 180, that's times 3. That's okay. If you're thinking of that way, you are correct. You are thinking correctly. That is, the answer is going to be 3, but here's how we can solve that without having to think about it that way. Cross multiply. 1 times 180 is 180. And then divide by the last number. 180 divided by 60 gives me 3. So 180 minutes means 3 hours. This works for any unknown, any type of unknown. I'm saying these out loud, but think of these as word problems that you might come across on the HESI. I just said out loud, I said, well, 1 hour is 60 minutes. Well, how many hours is 180 minutes? And that might be worded a little bit differently with a little bit more detail, but that's essentially what we're doing, is we're saying what I know about something, and I want to convert it to what I don't know. Just keep in mind of those, those units. However we set this up. If I'm writing hours over minutes, this side has to be hours over minutes as well. Measurement conversions work this, all the same way. So that was measuring time. With inches and feet, we were measuring length. As you guys get into nursing, you guys are going to get into medication measurements, where you're having to convert like teaspoons and milliliters. So we'll get into some of those. Let me give you some of those. The best thing I can advise you guys to do is look up what those knowns are. How many milliliters are in a teaspoon? How many milliliters are in a cup? Those kinds of things. In fact, those of you guys that are getting ready to take your HESI here at ATA, I will provide that to you guys. You won't be able to use it on the HESI, but just as you're studying, get to know what those equivalents are, or again, what our knowns are going to be. Okay, and I'll go through a couple of those and some familiar ones that you might see on the test as we go through some sample problems right now. So I'll tell you guys right now, 1 teaspoon. So you guys a lot of these might be similar to what we use in the house, what we have in our kitchen. right? Our teaspoon is a small spoon. That's actually equal to 5 milliliters. So if I needed to convert that, let's say I'm going to give a scenario. Okay, think of this in terms of a word problem. Let's say doctor orders a patient to take 25 milliliters of Tylenol before bed. Okay, and we think milliliters, okay, but makes more sense to us to convert that to teaspoons. So here's what we have to do. We have to think of that in terms of our known versus our unknown. So the question was 25 milliliters is how many teaspoons? So let's set that up. If we wrote down our known, 1 teaspoon, we know is 5 milliliters. Our unknown, keep in mind, is milliliters. So I'm going to put that on the bottom to go across from milliliters here is X amount of teaspoons. I want my teaspoons across from teaspoons, milliliters across from milliliters. A lot of people will instead of writing it down with the known first, you could have just started with your question. I have 25 milliliters and I want to know what that is. Oh, whoops. X amount of teaspoons. If you did that, that's okay. Write down the known. My known is right here, but remember, I want to put my milliliters on top and my teaspoons on the bottom based on this. No matter how you set it up, think about how we solve this. Wherever X is, we're cross multiplying the opposite side. So in our case here, 25 times 1 and dividing it by 5. Even if I set it up this way, since X is set up here, it's 25 times 1 divided by 5. Doesn't matter how you set it up, as long as 2 components are taking place here, or 2 things are being done. One, you have your known on one side and your unknown on the other. You can't separate the known. You can't have 1 on one side and 5 on the other. 1 and 5 in this example, 1 and 5 have to be the same fraction because that's your known. They have to be on the known side. Your unknown is 25 and X. So 25 and X are the unknown. So they have to be on the other side. You can see that's what I did in both scenarios. I have my known on one side, my unknown on the other. And this one, I just put my unknown down first. That's okay. It's just unknown on one, known on the other. That's okay. As long as I'm not separating the 2. And then I need to make sure that the units match up correctly. If I have teaspoons on top, the other side also has to have teaspoons on top. If I have milliliters on top, the other side has to have milliliters on top. Remember, it's showing an equivalent relationship. So if I have teaspoons is to milliliters as milliliters is to teaspoons, that doesn't make any sense. It has to be the same. I'm showing teaspoons is to milliliters as teaspoons is to milliliters. Over here, I'm showing milliliters is to teaspoons as milliliters is to teaspoons. Both are correct. Both give us the same answer, the correct answer. If I mix those up, I might not get the correct answer. So make sure that we're doing those 2 things with proportions. Like I said, known equal to unknown. Okay, so known on one side, unknown on the other. And then make sure your units match up. Okay. So get to know some of those measurement equivalents, I should say. So again, cups, ounces, milliliters, teaspoons, tablespoons, pints, gallons, quarts, be familiar with all of those because you're going to see those on the HESI. So make sure we just kind of study those. What 1 teaspoon is how many milliliters? 1 tablespoon is how many milliliters? 1 cup is how many milliliters? 1 cup is how many ounces? 1 cup. One thing that you'll see pretty common is 1 cup is equivalent to 8 ounces. So if I have a patient that drank 4.5 cups, I need to know what that is in ounces, maybe, because maybe I'm adding together how many ounces my patient took in. Well, let's write that down. If my patient had 4.5 cups, I want to know what that is in ounces. Well, remember, my relationship for cups to ounces is right there. So 1 cup is equivalent to 8 ounces. So to figure out what that is in ounces, I'm simply going to take 4.5 times 8. What is 4.5 times 8 exactly? 36. So we had 36 ounces today. Because 4.5 times 8 divided by 1. And some of you guys may be looking at this and say, if that's my question, you may not even take the time to set this up. And that's okay if you don't use proportions. Sometimes you can do that by just saying, well, I know that 1 cup is equal to 8 ounces. So if they had 4.5 times this number, they had 4.5 times this number. So you may just know to take 4.5 times 8 in that scenario. And if that's the case, no big deal at all. No big deal at all. Again, that's the beauty of math, multiple ways to get to the same answer. Proportions are just helpful because sometimes you're multiplying by your known, sometimes you're dividing by your known. In the case where, you know, in that example, I said that my patient had 4.5 cups. But what if I said, well, I know that my patient took in 64 ounces. Well, instead, in that case, I'm gonna divide by the 8, right? Because 64 ounces, and I wanna know what that is in cups. Well, 8 ounces is in 1 cup. You can see I've set this up correctly because I have unknown, known, and then I have ounces on top, cups on the bottom in both cases. So all I'm gonna do is cross multiply. Cross from my X here is 64 times 1 divided by 8. They had 8 cups. 64 divided by 8 is 8. So again, sometimes you're multiplying by that 8, sometimes you're going to divide by that 8. But the proportions are pretty helpful because it kind of guides you to show you which one. You know, you don't have to think about the difference between the two. Okay. Hope that helps with those measurements. Okay. I'm gonna go ahead and stop this video here and make a second video. So let's just call this our fractions, ratios and proportions and measurements, and then I'll create a second video for the others just to make sure that we've got those divided up a little bit differently. Okay, so we're gonna stop here and I'll see you guys in the next video.